So can I start now?
Yes, please.
Okay, sir. Good evening, everyone. Myself Aishwarya CL, and I welcome you all to the first section of 8th School on Climate Science and Policy. I hope all of you enjoyed Dr. Akhilesh Gupta's igniting thoughts on climate studies for future students. Those who missed the inauguration session can see the video from YouTube. So today we have Professor Eldho. Dr. Eldho is a professor and former head of Department of Civil Engineering, IIT Bombay. He has 30 years of experience in the area of water resources and environmental engineering as a scientist, professor, and consultant. He works in the areas of fluid mechanics, coastal hydrodynamics, and climate change impact on water resources, CFT, groundwater flow, and contaminant transport. He has guided around 32 PhDs and 5 postdoctoral fellows and 55 master theses, and presently guiding 10 more PhD students in various areas. He has published more than 500 research papers in various international journals and conferences. He has developed and offered 25 courses and a number of short-term courses for college teachers and working professionals. He has also developed 2 popular video courses on fluid mechanics and watershed management. Professor Eldho serves as an editor, associate editor, and editorial board member of a number of Indian and international journals, and has worked as a review editorial board member of a number of Indian and international journals, and has worked as a reviewer for more than 50 national and international journals in the recent past. He is also a research proposal for more than 50 national and international journals in recent past. He also research proposal reviewer for many research in organization and delivered several invited keynote lectures at various national and international organization and conferences. Dr. Eldho has co-authored 2 popular textbooks and contributed 15 book chapters in various edited books. He is recipient of many prestigious awards, including eminent water resources scientist constituted by Indian Water Resource Society in 2018. Welcome you, sir.
Okay, thank you, Aishwarya.
Thank you, sir.
All participants, very good evening and welcome to this 8th School on Climate Science and Policy, which is yesterday was inaugurated, and that will be continuing another few more days. So the first lecture which you are going to hear is from me only. So as Aishwarya already introduced about me, I will not go further on about me, but I am working this area for last 10 years, especially on climate change in the area of river basin scale, especially hydrology is concerned. So today's topic is climate change impact studies on river basin scale hydrology. So as all of you, how is recently, I mean, last few days, you would have seen in various newspapers and media about the CMIP 6 reports and the assessment report 6, and then its various contents you have seen. So as we have already observed, so there is a major issue of climate change which is going to come, and then various issues we have to deal as the climate change is going to be, so it is a reality, and then it will be continuing for a long time, and we have to take appropriate actions. So that way, this course is very relevant, and various aspects of climate aspects and climate science and policies will be discussed in the coming lectures. So anyway, this first lecture is on the hydrology. What are the impacts on hydrology is concerned? So as all of you know that say water is life. Without water we cannot live. So that way you can see that so whatever the impacts of climate change on water resources or hydrology. So it is a very, very important question, and the past few decades of studies showed that it's a very severe impact is there on hydrology as far as climate change is concerned. So today's topic is on climate change impacts on river basin scale. So why river basin scale? Of course, I would have presented for the entire country or for the particular region is concerned, but I am concentrating on the river basin scale, since that is, as a hydrologist is concerned, river basin is the fundamental unit on which we do all the water resource assessment and all the aspects as far as the hydrology is concerned. So that way, it is very relevant and very important to do appropriate assessments as far as the climate change say related to river basin hydrology is concerned. So in this topic, first we will have a brief introduction, and then we will be looking to various aspects of climate change and its impact. So especially in types of hydrological impacts, and then we will be discussing why we need to go for hydrological modeling. So as I mentioned, since hydrology is so complex, so especially if you take a river basin, large river basins, so river basins can be very small to very large, like it can be even of say 500,000 square kilometer above, or it can be 50 square kilometer. Like that, it can be very small to very large. So what are the implications, say, of climate change with respect to hydrology is concerned on a river basin scale? We need models. So hydrological models are essential. So in this lecture, main emphasis will be how to utilize specific hydrological models for climate change impact assessment. So then we will be looking to how we do the modeling of impact assessments, and then we will be further discussing a case study, a detailed case study we'll be discussing here to show how we can do these kinds of studies. So if any one of you, those who are interested to do further research or studies like this, you can take this into account, how we are going to do such studies, and then how we get the results, and then how we interpret it. So that will be the main theme of this lecture, and we'll be concluding with a few remarks as far as the climate change impacts on hydrology is concerned. So as all of you know that, so water availability, though we have got so much of water on earth, but water usable is hardly 1% is the water usable by humans. Even the so much water, I mean, say the remaining water, whatever is there, maybe in glaciers. So of course, say you can see that seawater is say large amount, and then whatever is available. So to humankind is only 1%, and out of this 1%, even mostly 99% is in the groundwater, and 1% is actually what is available for surface water in terms of rivers, lakes, and then what is we can directly extract as far as our utilization is concerned. So that way, water resource is very much affected with respect to the various climate change or other aspects. So when we look into water resources, the main issue is that these things are changing. I mean, whatever say the availability of water, or with respect to rainfall, or whatever is happening, that will be keep on changing with respect to space and time. So say for example, in India, we have got a monsoon starting from June to say September, October, and then next 4 to 5 months, all the rains happens, and then there is no rainfall, say afterwards. So that way, say next 7 to 8 months, we have to deal with whatever is what we got through the rainfall. So that way, it is so important to study, say using a particular hydrological model, what can happen on a river basin scale, on a state or a region scale, or the total country. So that is the major issue as far as hydrology is concerned, this spatio-temporal availability of water on earth and its variations. So now, as I mentioned, so water availability is so important. So now, if you look into, say, for example, as per the past studies, say freshwater availability now and by 2050. So even though this study was done by 2000, so you can see that country-wise, so huge variations you can see. Say, for example, in India is concerned, if you are having, say, for example, say around 2000 cubic meter per person per year, say by the year 2000, now it has drastically reduced, and by 2050 it will be hardly 1000 meter cube per person per year. So that way, so then the impacts of climate change comes. So though, since water available is so low, and the climate change impact also in a severe way coming to picture as far as hydrology is concerned, that will be a major challenge and a major issue as far as available water resource is concerned. So that way, we need to study what are the impacts of this climate change on a hydrological, as far as hydrology is concerned, and especially a river basin is concerned. So why river basins? As I mentioned, river basin is the scientific unit through which we can do all kinds of water resource assessments, and so with respect to climate change, what is happening, it is much better to study on a river basin scale. So coming back to climate change, as all of you know that the difference between weather and climate. So weather means conditions of atmosphere over a short period of time. So like daily, weekly, or monthly. So today it may rain heavily means, so it is only say today or tomorrow like that. So within what is going to happen immediately or what happens last few days. So with respect to that is what we call it as weather. But climate is concerned. So this is when we look into, we are looking for the what is happening long time. So climate means how the atmosphere behaves over relatively long periods. So generally, in all this analysis, you take 30 years for climatological studies. So now, say for example, if Chennai has a very hot and humid climate nowadays, so compared to say, so when we assess, so when we analyze last 30 years, so it is that what is the behavior, what is happening. So that is what we call it as climate. So then coming back to climate change. So climate change, as you can observe, so it is any systematic change in the long-term status of climate elements, such as it can be, so as far as hydrology is concerned, generally we talk about temperature, and then of course climate change is we are mainly on the temperature increase, and then due to the GHG gases like carbon dioxide. So such as temperature, pressure, or winds sustained over several decades or longer. So as I again mentioned, compared to mid-20th century, so if we say that Bangalore is becoming hotter, so that is the reason is that is what we say as climate change. So now the climate system is concerned. So here, so you can see that it is a complex system. So atmosphere is there, hydrosphere is there, and biosphere and geosphere, and all these interactions we need to study. So that is the climate issue is concerned. So luckily we are having global circulation or general circulation models are with us, so which we can effectively utilize to study in terms of what can happen. It can be with respect to changes in temperature, changes in precipitations, and then change in pressure variation or winds. So all these things, what is we call it as climate change. So now, say climate change, as you can see that we are feeling now this climate change last few decades, and then what are its impact? So the climate change at its impact is it is a long-term shift in global or regional pattern, as I've already mentioned. So often climate change refers specifically to the rise in temperature. So as all of you know that mainly we always talk about the rise in temperature. So that is now we have already identified that this is due to greenhouse gas emissions and then industrialization that has happened last 1 century. And then so of course other than that, say the anthropogenic effect, like what are the land use, land cover changes, so that is happening, that is also contributing as far as the climate change is concerned. So as you can see that within the perspective of climate change, there are so many impacts we can observe, and so much of studies are going on. So that can be in terms of hydrology, like floods, or lack of availability water, say like droughts. So that can be, or just you can see that say now in US you read in newspapers for forest fires, or in Australia last year or 2 years back, and then all these kinds of issues can come. So these are some of the impacts as far as climate change is concerned. So as you can see here, the greenhouse gas, and then what is happening is very clear with respect to some of the infrared radiation is absorbed, and then the atmosphere is heating up, and that are the main impacts. So what are the effects, after effects we can see from this climate change? So as I mentioned, mainly what we can feel or what we can observe directly is the change in temperature. So you can see that say now these results are from assessment report 5, which was published in 2014. I will show what is there in 2021, what is published in air CMIP 6 also. I will just have a brief introduction, but most of the studies what I will be presenting is with respect to the CMIP 5 reports, and then corresponding the assessments. So here, as you can see that so global average surface temperature changes. So you can see that So generally this in the last assessment report with respect to AR5, so generally we'll be putting in terms of RCPs, so which is we call it as representative concentration pathways, so RCPs. So generally, so the best possibility is 2.6, and then so if the current way it is continuing, then it can be RCP 4.5, and extreme condition is 8.5. So if you look into mainly say so some of the issues, as I mentioned, say the daily climate change, what is happening, which we can feel or we can observe. So one is the temperature change, then second one is the precipitation change or related issues, and then third one is the sea level rise. So all this comes together, then you can see that so that is what we are going to discuss in terms of hydrology, especially hydrology is concerned, how it is going to affect the hydrology, and then especially river basin scale hydrology is concerned. So as you can see here in RCP 8.6, it can be keep on increasing, it can go beyond 3 degrees centigrade if it is going to RCP 8.5. But if it is 2.6, then it will be, say, we can pull down to below 1 degree centigrade. But if the same trend, current trend goes, it can be RCP 4.5. So that will be in between these. So that is what is generally the way we analyze. So here you can see that correspondingly, as projected by the IPCC, so global mean sea level rise. So you can see that if you study from say 2000 onwards, so what is happening, you can see there is a trend in the sea level rise. So here you can see what is happening now, say 2020, and then you can see that it is with respect to RCP 8.5, this line, and then this is RCP 4.5, and then below you can see that RCP 2.6. But what we say generally in this kinds of assessments, we are much bothered about RCP 4.5 and 8.5 and the corresponding projections. So now that is about the sea level rise. So you can see that say even last few decades already say 30 centimeter to above the mean sea level rise is observed, and that is already reported by many researchers. And then next one is change in annual precipitation over the land. So you can see that there is a huge changes are observed. So here this shows the observed precipitation change from 1901 to 2010 as per IPCC AR5 report. So you can see that what is happening, some locations it is say increasing, rainfall is increasing, some location it is decreasing. So that kind of trends we can see what is happening as far as the precipitation, annual precipitation over land is concerned. So as I mentioned, the last few weeks we are discussing about the IPCC reports, AR6 reports, CMIP 6 reports. So here the details are available now in their websites. So here you can see that future emissions cause future additional warming with the total warming dominated by past and future carbon dioxide. So you can see that in this now current assessment, as per current assessment report, instead of RCP, so the IPCC is putting as the shared socio-economic pathway. So SSP. So here SSP 1, 1.9, SSP 1, 2.6. So this is what is related to RCP 2.6, and then SSP 4.5, so almost similar to RCP 4.5, and then this is similar to RCP 6 or 7 between that, and then this is 8.5, the severe condition, SSP 5, 8.5. So correspondingly, what can happen in the near future up to 2040, 2016, mid future, long term future, what are the temperature changes also reported as you can see here in the IPCC report. So here the contribution to global surface temperature increase from different emissions with a dominant roll off. So you can see that this first one, this is a total change, and then the second one is this is due to carbon dioxide. So that is you can see all these details available in this website. So now as we are discussing about hydrology, so we are mainly bothered about the global surface temperature, and then we look for the annual the changes with respect to temperature and the precipitation. So as per these CMIP 6 reports or AR5 reports, you can see that when we look into 1850 to 1900, 1900, and then correspondingly simulated change for 2 degrees centigrade global warming. What are the changes possible related to the precipitation? You can see. So most areas, it is as per this current assessment report, there is a possibility of more precipitation, as you can see, if the temperature is going for 2 degree rising, and this is the situation by 2100, and then simulated changes with respect to 4 degrees centigrade with respect to what is happening with respect to 1900. So then annual mean total soil moisture, accordingly all the changes will be happening. So that is why it is so important that we need to study all these aspects. So that is about the climate and climate change and what are the possible impacts. So coming back to our topic, so on hydrology, what are the impacts on hydrology? So that is mainly our topic. So here last few years, say for example India is concerned, we can see that in every year we can see severe flooding in one or another part of the country. So for example, say starting from Bihar 2004, then Mumbai 2005, so like that in Bihar and all places. The latest, the last one, I mean 2018, which was very severe flooding. You can see this photo from Kerala 2018, and this year also we are seeing flooding in Bihar and other areas. So that way, the question is whether this increasing extremes, whether this is only due to climate change or due to climate change and land use, land cover changes. All these things we need to assess appropriately to see that say how it is happening and what are the causes and what are the way, and we can say how much impacts are there, and then what kind of mitigation measures are possible. So that is why as far as hydrology is concerned, we need to look into. So coming back to the climate change impacts, factors affecting, say for example, as I mentioned, two important aspects. One is flooding, hydrology is concerned, and another one is possibilities droughts or related conditions. So here, large volumes of greenhouse gas emissions, as we have already seen earlier. So melting of glaciers, thermal expansion, then change in evapotranspiration, change in snow accumulation condition, all those things happens. And then there can be increase in river flow rate. So then change in water use pattern also takes place. So that way you can see that what will be the consequences will be more frequent storm surges and coastal erosions. So whenever the sea level is also simultaneously rising, then we can have more frequent floods, more serious landslides or debris flows, and then of course, as you can see that what we have, all the studies shows that whenever precipitation happens, it happens for say short duration and high intense rainfall. So that is the cause of flooding, and afterwards there is a quite lean period, and that is the high risk of droughts. So droughts possibilities also increasing. So these are the main observations as far as all these studies are concerned. So now coming back to hydrology, since that is our main emphasis of this lecture is on hydrological implications. So as I mentioned, increase in temperature means we can have so evapotranspiration can increase, and then the water quality, say the total water quality can be affected. So then with respect to this change in precipitation patterns, we can observe with respect to the total runoff will be affected, the stream flow will be affected, and water availability will be affected. So as I mentioned earlier, so there is the rainfall intensity will be becoming higher, and then frequency and magnitude of floods and corresponding that will be say by high intense rainfall means the frequency and magnitude of floods will increase. And then as I mentioned, whenever precipitation happens, it is happening in a high intense way, and then afterwards there is no rain, so that can lead to droughts. And then of course the implications are concerned. So what can happen is with respect to this all these changes, the groundwater, as I mentioned, a major source of water, so that will be also affected. Groundwater recharge will be affected, and then rise in sea levels can lead to inundation coastal areas, and then also the salinity intrusion. So these are some of the hydrological implications as far as the climate change is concerned. So now coming back to our topic, so here, as I mentioned, the hydrology is so complex, especially river basin scale hydrology is so complex. We need to deal with many aspects. So it is not only the uncertainties with respect to the rainfall or precipitation and all of the other parameters, but we need to also we are dealing with the large scale areas. So for example, say a river basin, as I mentioned, it can go from say small river basins like 50 square kilometer to it can 500,000 square kilometer area. So that way we need to have appropriate models. So it is not only the climate change aspects, like general circulation models gives the temperature variation, the precipitation variations, all those things we can downscale, and then we need to have an appropriate hydrological model so that we can assess what will be happening. So here, the assessment of impacts on water resource due to change in land use, land cover, we need to assess changes in climate variables, physical structures. So for example, if you are having so reservoirs and dams, so then so if the climate change happens, then if the pattern, the hydrological pattern changes, so what will be the impacts? So all those things we can only assess through hydrological modeling, including diversions, pollutions, and erosion. And then say for example, so as I mentioned, we are observing that there is possibility of the increase in precipitation in future. So that way we need to project what kind of extremes are possible, so that say some kinds of mitigation measures or the policy decision makers can start work on it. So that way flood forecasting or disaster management and droughts. So here in all these hydrology is concerned, the design needs how much flow will occur, say for example in a 100-year storm, what will be, say how much flow will take place, and then how it is going to, say the flooding or how it can happen, and then how much water is available, and water quality, all these aspects we need to study in detail. Am I audible and everything is fine? Hello?
Yes, sir, you are audible.
Okay. So now if you look into the hydrological modeling is concerned, so as I mentioned, hydrology is so complex, we need to go on a systematic way, then only we can get appropriate results. So we need a lot of data, so that is the major challenge as far as hydrological modeling is concerned, like database structuring, meteorological data, geographical data. Then if we cannot directly collect the data, then say we need to retrieve the data from the available sources, like now we can use satellite data also, including for precipitation or the temperature variation, all those things we can use the satellite data, and then we need to retrieve it and process it properly. So that is first aspect is data. So that is in the hydrological modeling is concerned. And then second aspect is the what kind of models we use. So there are plenty of models. So last say so many decades, so different types of models have been developed, and then we need to choose appropriate model for say particular study is concerned. So for example, if you are going only for surface runoff, then say like SWAT or some kind of model will be possible. But if you need to also study the groundwater, then say how the interaction between surface water and groundwater takes place, then we need to choose other models, like say whatever is connected SWAT coupled with the mode flow, or that kind of models are needed. So we need to say simulations, hydrological simulation is concerned, we need to look into what is the model choice. Then of course, so as I mentioned, the data is a major issue. So it is not only the climatological data, but the geophysical data, geographical data, like the soil data, the land use, land cover data, all these data are needed. So that way there is a lot of uncertainty will be there. So that way the appropriate model, the model which we are doing, we need to do the calibration and validation. So on a river basin scale, so for example, to validate a hydrological model means we need to collect the the runoff data or say the river discharge data, and then say we need to run the model, and whatever the model is giving with respect to precipitation, whether it is giving in the right way. So then next one is model run, and once we are having appropriate model, then we are using the output of the model, we can go for impact assessment, and from that impact assessment we can go for adaptation or mitigation strategies. So that way the hydrological model is so essential to understand what is happening, and then with respect to especially climate change, how we can do this. So that is what we are going to demonstrate through a case study. So now the hydrological model, as I mentioned, a number of models are available. So what kind of model you should choose? So that is some of the important questions coming here. What time scale are you working at? So whether you are looking for a daily scale model, or like weekly or monthly, or even say, for example, flooding is concerned. So flooding, if you take say monthly or weekly, there is no meaning, since floods happens only for a few days or a few hours. So we need hourly basis simulation, and so that we can understand how the flood is propagating and what kind of damages, or we have to prepare the flood hazard map, and then corresponding the risk assessment to be done. And then what hydrological quantity are you trying to obtain? So as I mentioned, whether you need only surface runoff, or you want to get to the evapotranspiration, surface runoff, then base flow, all the aspects are required as far as hydrology is concerned. So that is another question. And then so another important question, as I mentioned, what kind of data you are having. So say, for example, most of the time when you are dealing with large scale areas, so we need a deep elevation models, then appropriate land use, land cover models, and so then soil map, all these details are needed. So that is another important question. And then you see that now, though computers, fast computers are nowadays available, even available PCs we can directly use for these kinds of studies. But when we are looking for long-term simulations, we need a high-end computer, like high performance computing is required, especially climate changes studies. So now, as I mentioned, there are number of models are available. So hydrological models, there is say like models can be deterministic or empirical or lumped or physically based model. So here a number of models available I have listed here. So like a distributed model like a MIC. So if you are looking for modeling soil moisture, irrigation, command management, so there we need to have such a distributed model, especially if flooding is what we are going to study with respect to climate change impacts or whatever it is. So then we need to use MIC. But that model, MIC is concerned, we need to pay for that. It is say we have to buy the model. But open source model like SWAT we can use. So SWAT is concerned, it is soil water assessment tool. So we will be discussing a case study using SWAT. So here we can get water balance, sediment, then stream flow and non-buoyant source pollution. All those aspects we can get through the SWAT model. And then we have other models like hydraulic simulation model, topographic model, agriculture non-buoyant source model, then watershed modeling systems. So like that. So we need to decide what are our objectives. So accordingly, we need to choose appropriate model for the. So for example, if you want to only assess the surface runoff and then its related aspects, then model like SWAT is good enough. Or then we need to go for further various aspects for the various components like irrigation, command management, then all those aspects, then maybe MIC, or so depending upon the objectives of your study, we need to see particular model, a hydrological model is concerned. So as I mentioned, so for any hydrological model, so since we are dealing with the large scale area, so we need to have an appropriate DEM. So that is deep elevation model is very important nowadays in all these kinds of modeling. And then since hydrology depends upon the land use, land cover pattern also, so the land use pattern we need to get, that data is required. And then since say the hydrology is concerned, precipitation, once it happens, it can be evapotranspiration, then infiltration, all this process takes place. So that way soil data is very, very important. And then with the climatic data, so these all will be leading to so we can develop using all these data, hydrological model can be developed. And then we can go for impact assessment, what is happening. So the impacts can be whether it is long-term impact or short-term impact. And then accordingly, we can go for mitigation strategies for long-term. And then short-term means immediately we need to what kind of adaptation strategies are required. So that way we need to look into. So now coming back to hydrological model applications, so there are a number of applications. So rainfall turnover models like simulation prediction, then surface water, groundwater assessment, flood drought predictions, evaluation of watershed catchment management. So like that, including environment impact assessments, we can do using the hydrological models. So now we are coming back. So now we are going to see how we can get to the climate change impacts, say as far as the hydrology is concerned, especially on river basin scale. That is the main topic which we are going to demonstrate through a case study. So here, as I already mentioned, the present study will be using this RCP scenario, especially in the study RCP4.5 and RCP8.5 will be the assessment, the scenarios what we'll be doing. But as I mentioned, currently that AR6 report 2021, so here shared socio-economic pathways. So here correspondingly we can say that this is this and then this. So that way the changes are taken place, but still we are using these RCP scenarios. So when we look into, say for example, in a country like India, so what are the issues to be addressed? So that is, as a researcher, as a student, as a professional, you may ask what are the issues. So here some of the issues I have listed. So we need to see the water availability. So how do water fluxes vary on catchment scale, especially with respect to climate change, what can happen, and then say whether sufficient water will be available on river basin scale. So you can see that river basin scale map here. So then we will be observing what water quality issues, and then say change of frequency or magnitude of extreme events. So as I mentioned, the floods and droughts. So what will be the impact as far as the floods and droughts are concerned. And then design storm intensities like urban flooding, especially urban areas is concerned. So we have to use a very sophisticated model. So we need a high resolution model so that a small area what can happen. So that also we need to study. And then delays of onset monsoon. So hydrology is concerned, as you can see, a country like India, or more than 60 or 65% farmers depends upon the monsoon. So we need to see what are the impacts on agriculture. So the monsoon, say whether it is starting the onset of monsoon, whether it happens especially June 1st week, or whether it is delaying, what will be the impact. Then over year storage policies, then real-time adaptive decisions. And then the other issues are like water demand. So on a watershed scale, on a river basin scale, so you can see that evapotranspiration, then municipal and industrial demands, and then irrigation demands, all those things we need to meet. And then especially we have got a very long coastal region, so that way we need to see the salinity inclusion or coastal flooding, what are the possibilities, so that we need to see. And then so that way the hydrological impact studies are concerned, we need to have robust and resilient water so all the studies can lead to robust and resilient water management policies to offset adverse impacts due to the climate change. So that way climate change impact on water resource or hydrology is concerned. So the hydrological, so as I already mentioned, both the AR5 and AR6 reports indicates, especially in a country like India, the hydrology cycle is predicted to be more intense with higher annual average rainfall as well as increased drought. So as I mentioned, when rain happens, precipitation happens, it will be high intense rainfall happens, and then afterwards there will not be any rain. So that way there's a possibility of increased drought also. So there is a predicted increase in extreme rainfall and rainfall intensity, and intensity of rainfall is predicted to increase. So that way, and then surface water availability showed a general increase. Then that way, what are the policies are concerned, what are the policy implications of all these projections or predictions. Then changes in precipitation can affect a variety of planning issues such as planning and design of hydraulic structures. If you have got a dam, it's a reservoir, there is no water, then there is no meaning. So, but if it is when heavy rain takes place, it is filling so fast, and then we cannot use for a long time. Then we need to release the water from the reservoir. So that kind of issues. So that river basin management is very essential for flood control and drought management. And then urban areas concerned, we need to see for urban planning and management is concerned. So we need to see within this context also what will the impact on related agriculture. Then say if say around 15% in India we produce hydropower. So what will be installed power capacity? What kind of changes can take place? Then environmental flows in the dry season, how it is going to affect. Then higher flows during the wet season. So that also we need to study. So that way, when we look into the predicting the climate change impacts on hydrology, so we need to see the climate scenarios. As I mentioned, it can be RCP or SSP, whatever we are looking. Then of course, as I mentioned, we are dealing the land, the watershed or a river basin. So what are the changes that can happen land use pattern? And then we do the hydraulic impact modeling. And then from there, we get to the projections, possible future hydraulic scenarios on basin scale. So we start with like climate change with the GCMs, global circulation models. That way we can use it, as you can see here. And from there, we need to go for, since most of these GCMs are say 2.5 degree or above resolution. So we need to get to higher resolutions like 0.25 or 0.1 degree resolution we need, especially for river basin scale analysis concern. So we need to go for regional climate models. And then climate change scenarios, we can get it. And then, as I mentioned, we go for hydrological models. So it can be for river runoff scenarios or sedimentation or nutrient runoff or sea state scenarios. All those things we can do. And correspondingly, the impact assessments, we can do it. So the climate change impact on water resource, as I mentioned, so we get all the data and then do the corresponding assessments, and then the hydraulic impact modeling. So generally, we'll be looking for precipitation, water yields, the changes in the active evapotranspiration, then sediment yield, drought analysis, and then of course city level or urban areas flooding or what will be happening. So now we are going to discuss further the climate change impact assessment modeling. So as I mentioned, so am I audible and everything is fine, Aishwarya?
Yes, sir. You're
Okay,
audible.
so now we are going to discuss the climate change impact assessment. So how we use the GCMs, general circulation models. So this is the best tool we can use for especially the climate change impact as far as future is concerned, how it is going to impact. So here this GCMs what is developed is accounting for greenhouse gases in the atmosphere that can simulate large scale circulation patterns. You can see a total grid wise it can get. So it is do not produce well non-smooth fields such as precipitation. So there is, as I already mentioned, there is a scale mismatch. So most of the GCMs are more than 2 degree or above, but the hydrology is concerned, we need to come to further, we need a downscaling. So climate models are systems of differential equations. So this anyway, I'm not going to discuss. You can see that the GCMs consider all kinds of details like the loss of physics, fluid motion, chemistry, and then the winds, heat transfer, radiation, all the aspects are considered. So now, say for example, as per AR4 report, climate change, all the scenario, so many of you may be knowing it was A1B, A1T, like that, A2B1, these kinds of scenarios were there as per IPCC 2001 reports. Then came the RCP scenario, as I mentioned earlier. So here 2.6, 4.5, 6, 8.5. So correspondingly, description. So here, as I mentioned, a reduction scenario in which significant GHG mitigation policies implemented, like Paris Agreement, what is happened in 2018. If we can go to that level, then RCP 4.5 will be valid. But extreme condition is RCP 8.5, a very high emission scenario. So correspondingly, we have already discussed. So the latest 2021, the scenarios are with respect to shared socio-economic pathways. So here, say RCP 4.5 almost very similar to for SSP2 or 4.5 and SSP 8.5. So we will be discussing with respect to RCP 4.5 and 8.5. So now coming to hydraulic impact assessment, as I mentioned, scale is always an issue. So here these GCMs are concerned, large scale models are there. So here, but the GCM's ability declines when it's coming to small scales. So the hydrological studies are concerned, we need say 0 to 50 kilometer like kind of studies. So it can be 0.25 degree or 0.1 degree, that kind of studies. So that way, we need to downscale the data. So GCM's ability declines when small areas are concerned, but hydraulic importance highly increase as far as the small areas are concerned. So that way, we need to go for downscaling. So downscaling, you can see that what can happen is with respect to this grid, we project to the area which we are looking for, and downscaling can be. So here you can see the grid size from 2.5 degree to 0.2 degree or 0.1 degree. We have to downscale, and then we have to utilize that data. So downscaling is concerned, it can be two kinds of downscaling generally we use. One is dynamic downscaling, second one is the statistical downscaling. So what we do, we in dynamic downscaling use complex logarithm at a finer grids, like regional scale more climate models we can make from the GCMs, and then we can directly use that data. In statistical downscaling, we are using the past data to produce future scenarios based on statistical relationship between large scale climate features and hydrological variables. So here assumption is statistical relationship holds good in future for change the climate scenario. So here advantage is that it is computationally simple, but we need a bias correction. So that is very important since with respect to past data. So that way, important climate predictors must be reliably simulated by GCMs readily available from archives. So we can do this downscaling, and then we can use it. So now, say for example, as I mentioned, I am going to present a case study with by using the CME 5 RCP scenario, but CME 6, what can happen? A study published by Professor Vimal Misra and his team in the journal Scientific Data. You can see what can happen before bias correction. So this is what is why bias correction is important. So here before bias correction, you can see how the precipitation maximum or minimum temperature, and then after bias correction, what is the reality. So bias correction is very, very important in as far as the climate change impact assessment is concerned. So we will be generally using as far as hydrological model, we need to use the bias corrected data, so that we check for last 20 or 30 years data, we use it, and then we get a reasonable good match, and then we can use that GCM data for further hydrological modeling and studies. So here, say for example, this what is happened with respect to this the studies. There are two studies which I have just seen recently. One is another Professor Misra studies, and another one is published in say Earth system dynamics. So robust increase of Indian monsoon rainfall. So here you can see that SSP 4.5 to SSP 8.5. So in all those things, we can see that say what is the latest prediction also shows approximate 20 to 40% increase in rainfall. Mean annual precipitation can increase with respect to say for example 1901, and then similarly the precipitation, the annual maximum temperature also there is increase, and then similarly minimum temperature also. So those who are interested, please go through these kinds of papers, so which gives more details. But we are going to use the RCP 4.5 and 8.5 scenario, whatever the case studies which we are going to discuss now. So here projecting the climate change impact. So here what we get after the downscaling. So we run by using the topography and land use pattern and soil characteristics, we run the hydrological model, and then we go for possible future hydrological scenarios on basin scale. So here, as I mentioned, a number of models are available. So if you are going for the river basin scale studies, then soil water assessment tool will be very useful and very commonly used. And then if you are going for a grid-based scale or a region scale or for entire country or a global scale, we can go for variable infiltration capacity model. A comparison is given here. Actually, as part of a sponsored project from Jal Shakti Ministry, Government of India, we are doing a study for Tadri to Kanyakumari, say the climate change impact. So we are using both these models, BIC model and SWAT model. So I am going to present the results from a SWAT model study for river basin in Western Ghats region, southern India. So here these two models, one is both are semi-distributed model, and a spatial disaggregation here, grid sets, subgrids, the heterogeneity, where elevation and LULC data directly can come from the grid. And here SWAT is concerned, we use hydrological response unit. And then climate data input is concerned here for VIC model, we need precipitation, maximum minimum temperature, etc. Here also a very similar way. So here representation of soil, typically 3-layer soils is VIC we use. SWAT we can go up to 10 layers of soil data, so that all infiltration details can be taken care of. And representation of vegetation, fixed monthly plant characteristics can be taken care in VIC. In SWAT, the simulation of plant growth using EPIC growth model will be used. And here a potential evaporation VIC, they use Penman-Mondelith model. Here Priestley-Taylor model. So like that various option you can see here. So this is the overall sketch of VIC model and SWAT model. So VIC is concerned, we consider grid like this. And then with respect to these three soil layer, with respect to precipitation, how the evapotranspiration, all those things are studied in details. You can see I am not going to details of the model, but this is freely available, so you can download both models and then you can use it. So SWAT is an open source semi-distributed physically model, spatial scale river basin. So data organized sub-basin or hydraulic response unit. So time scale, it can be continuous time scale model, and based on a daily scale also we can run. So input required is topography, LULC, soil properties, weather and land management practices. So both these models we are used for our studies, but here I am going to present the SWAT model for a river basin scale studies concern. So now we are going to have a discussion on a case study. So here the case study is taken from the Western Ghats river basins in South India, which is called Valabhatna river basin, using the SWAT model. So for those who are interested, you can refer to this paper, so which we have already published, this journal, Hydrological Science Journal, and then also another paper in Netravati Basin. This is another journal which we paper which we have published. Those who are interested, you can go through this, how these kinds of studies are undertaken. So now this case study, we are going to discuss in detail how we conduct such studies, and then what kind of inputs are needed and what kinds of outputs are needed. So Aishwarya, am I audible and everything is fine?
Yes, sir. Yes, sir. You're audible. Yes, sir.
Okay, so this case study is Valabhatna river basin. You can see here, this is the location map. So here, this is the boundaries of the river basin. And correspondingly, you can see the land use, land cover, say for example 2014, and then replay elevation model. The elevation varies from 0 to, since it joins the sea. So here 0 to 1556, and here so the monsoon pattern. Say here the rainfall pattern is, say, mainly the monsoon rain starting from June to October, and then of course retreating monsoon also certain percent happens in this area. And this we are used NBS soil data. This is the details available. So here the details of the study area. So this is latitude, longitude is given here. So the river length is approximately 117 kilometer, and the drainage area is around 2,500 square kilometer. So here, as per 2014 land use, land cover basin is mainly covered by evergreen mixed forest, about 57%, and then followed by plantation and agriculture. So that kind of variations are observed. The average annual precipitation in the area is about 2,500 millimeter, and most precipitation, almost 82%, takes place between June to September month. So the average minimum maximum temperature is here 19.63, minimum and maximum is 29.12 degrees centigrade. So this I am systematically showing how you can collect all this data and do a hydrological impact studies with respect to climate change, and then what kind of data are required, and then what kind of output you can get. So as per the soil map, we are so here mainly agricultural. The soil is sandy clay loam and clay loam, so that is the soil data. And the land cover classes include forest, evergreen, and mixed agriculture kind of land use land cover. So here the studies, whatever we are doing is 3 types of studies we are doing. One is the climate was kept constant. As I mentioned, land use land cover change is a major issue, and then what are its impact as far as the climate change is concerned, so that we need to study separately. And then if LULC, land use land cover, is kept constant, so that is the first study. And second study is LULC is kept constant and climate was allowed to change. So whatever the data we are getting from GCMs, then we are running the model, and then we are getting what are the impacts climate, only climate is concerned. And then finally, what is the reality is that combined impact of land use land cover and climate change. So that is the final way. But we need to see since the land use land cover change is happening drastically in many of these areas, so we need to assess that also, so that we can show, yes, if the land use land cover change is happening like this, then what are these impacts. And then of course climate change case B, and then combined. So climate change impacts are analyzed using 5 GCMs as mentioned as part of this project. So here 2 critical scenarios, RCP4.5 and 8.5, are analyzed separately. So RCP4.5, as I mentioned, if the current trend goes, that means it is the gas emissions or the carbon dioxide, there is only small rise is there. But RCP 8.5, the extreme case. So the medium case and their extreme case, that is what we used in this study. To identify the impacts of future climatology, GCM outputs for a future periods were used in 3 time slices. So 2010 to 40, then 41 to 70, and 71 to 2100. So in the third scenario, SWAT model was run to obtain the baseline periods, say by taking 1985 2010 and projected for future period up to 2100 with the climate of 2030, 50, 75, 2100 with this land cover data correspondingly 2030, 50, 75, and 2100 kind of land data. So this flow chart, so you can see these details in our published papers, also the methodology and the overview of the work. So here we need the data like DEM and data, soil map, land use land cover map, observed the climate and other precipitation, temperature, all data, and then SWAT model. So similar to stream flow and sediment yield. So I am presenting only the runoff here, and then compare. Then so the SWAT model, we need to do a lot of calibration. So we use SWAT cup in Sufit model. So we adjust sensitivity parameters. Then if calibration criteria is satisfied, then our model is ready. And then scenarios are concerned, as I mentioned, the only land cover change, case A. And then we do up to 2100, and case B, only climate change by using land use land cover constant. And then finally, we do the assessment with respect to the combined impact of land use land cover change and climate change. So that is the way for RCP 4.5 and 8.5. So the source of data here, I have listed input data for SWAT model. So here we use the 30-meter resolution DEM. Land use map we got from Landsat imageries with respect to 30 meter, and soil type map is around 1000 meter. And then the meteorological data. So we are using the 2.5 degree scale, and the observed hydrological data, daily data, we are using on a grid scale. So here we use this is not Cortex project, sorry. Here we are using this five GCMs. So here this is what we are using. This is not Cortex project, sorry. This is wrong. The GCMs from the 5 Canadian GCMs, then Beijing Climate Center GCM. These are the 5 GCM which we are using in this study, and corresponding spatial resolution is given here, and corresponding scenarios are also given here. So first we need to see what is happening with respect to this whenever we are downscaling, and then so the statistical downscale products available we are using here. And then we need to further do quantitative map based bias correction, and then the comparison of historical observed and GCM simulator rainfall 1981 to 2005 and projection for up to 2100 you can see here. So here with respect to IMD data, directly what is it is we are getting reasonable match, and then only we are going for using various 5 GCMs as I mentioned we are using here, and we are getting a reasonably good match, and that is why we are using the same. So correspondingly here you can see the maximum temperature variations you can see here with respect to RCP4.5 and 8.5. So this is the ensembled one with respect to all these 5 GCMs. So here 5 GCM what are used already mentioned here. So correspondingly the ensembled one is shown here. So with respect to RCP 4.5 and 8.5, this is 4.5, this is 8.5. And this shows historically with respect to the minimum temperature variation also with respect to ensembled one. This is 8.5 and this is 4.5. So that kind of details are obtained. And here the climatology of rainfall. So with respect to, say for example, annual basis, how the changes taking place with respect to the rainfall. You can see here the rainfall and the with respect to IMD data, and then we compared with respect to various GCMs, and then we use the ensemble data. And similarly here you can see, so this ENS means the ensemble. So this is what we are using. So that we are getting a very good match. So that way we are using this GCM data. So this shows the Taylor diagram for rainfall T max and T minimum for the study area. So you can see that very good match we are obtaining. Say around the NSC value is 0.8 to 0.9 we are getting. So correspondingly that is why these GCMs we are chosen, and then these are used for the river scale river basin scale assessment. So here SWAT model is concerned, there is a large number of parameters are there. Like here I have listed 32 parameters. So many parameters are there. So we need to calibrate the parameters. So from this we have chosen around 15 parameters which are found to be very relevant as far as these kinds of studies are concerned. We have calibrated it, and then this shows the calibration and validation of the SAT model for stream flow. So you can see that starting from 1991 to 2000 data is used for calibration, and from 2001 to 2010 is used for validation. So you can see that a very good match after the calibration is obtained with respect to various SWAT parameters. So that way we have observed that SWAT can give up very good results as far as this river basin scale modeling is concerned. So then another question is, as I mentioned, land use land cover changes. So land use land cover changes. So it is not only the climate change, land use land cover change is also very important. So you can see here. So we used what we did. We got from the Landsat data. We got 1988, 2000, 2014. All this data were obtained, and then we use ERDA's models for the projection for the land use land cover projections. So here this shows the actual 2014 and projected, it is compared. So we got a very good correlation, and then based upon that we further projected the land use land cover for 2030, 2050, 75 and 2100, and that data were used. So here this river basin is concerned, it is say if it is 2014 hardly 5 to 6% is the urbanization, so it will be increasing around 14% by 2100. So that is, so this data which is projected land use land cover data is also used. So as I mentioned, three kinds of scenarios we are simulated here. So what is the impact of the land use land cover change only, and second one is what is the impact of climate change only by keeping LULC constant, and then the combined impact. So here this shows the spatial distribution of actually evapotranspiration with respect to, so this is the rainfall, the historical rainfall which we used for this assessment. So here 2030, 50, 75, 2100, how the variations are taking place. So this is 88 to 2000, 2014, then 30, 50, 75, and 2100. So you can see that the climate, compared to climate change, the land use land cover change impact is not that much, but still a lot of changes you can observe, since as I mentioned here, you can observe here a lot of land use land cover changes taking place. Accordingly, the evapotranspiration, spatial distribution, evapotranspiration changes, and then this shows the climate so the impact on the spatial distribution of surface runoff. So with respect to 1981 to 21, so 2000 and 2014. What is the changes taking place? Figure A. This is with respect to 81 to 2000, and then 2000 to 2014. Then that is the difference. This is only the difference is plotted here. And 14 to 2030. Then 14 to 50 and 14 to 75, and so up to 2100. So how with respect to LULC changes, what is happening, what are the impacts? So this shows the impacts changes in stream flow due to LULC changes, mean monthly, means seasonal, and annual in the Valavat River basin. So how much percentage changes taking place? So you can see the changes in stream flow. So here, especially summer rainfall is here observed, and then the big changes observed, especially summer is concerned. But monsoon season, there is not that much changes not observed. And then case B, second case is land use land cover is kept constant, say by taking 2014, whatever that is used as a base, and then we use the special distribution actual rainfall for this river basin obtained from that 5 GCMs. So here RCP4.5 near mid 2030, 70, then far distance, so 2001 to 40, and 40 to 70, 70 to 2100. So correspondingly 8.5 scenario, the rainfall is put into the river basin, the special distribution is obtained, rainfall, and then we kept the LULC constant and run the model. So here this shows the spatial distribution of actual ET evapotranspiration for near, mid future, and far future, how the system will be, how the changes will be taking. So you can see here also, compared to land use land cover change, here the changes are more, since the more in all this river basin what we analyzed showed that the climate change impact is more severe. And this shows the LULC is kept constant and climate is allowed to change. So spatial distribution change in future surface runoff of 3 different scenarios, how the variation is taking place for RCP 4.5 and 8.5. So that is shown in this figure. So then again, monthly variation, seasonal scale, how the changes. So you can see here, this area summer rainfall is this river basin, there is an increase is observed, and then monsoon there is a small decrease is observed. So like that kind of variation, monthly basis and also seasonal basis we can obtain. And then finally, we analyze the combined impact of land use land cover change and climate change. So that is shown here, special distribution of actual evapotranspiration shown near, mid, and RCP 4.5, 8.5 emission scenarios you can see here. So the combined with respect to land use and land cover change. So here evapotranspiration changes, then spatial distribution of changes and surface runoff for different scenarios up to 2100. So for 4.5 and 8.5. So for the near, mid, and far future. So you can see that severe impacts, especially RCP 8.5, you can see large impacts are visible. Then the combined impacts with respect to the monthly base also we have obtained, and corresponding seasonal wise also. So finally, the conclusion from river basin scale study. So it is found that stream flow is expected to decrease in the monsoon. So that though the projections are for entire India or various parts are differing, but small scales, when we coming to river basin scale, changes can be different. So that is what is observed here. Here it is found that stream flow is expected to decrease in the monsoon season and increase in the winter and summer season, along with some variation in future change. So due to LULC change, surface runoff will increase in 2030, 50, 75, 2100 by this much percent, 3.83, like that it is increasing. And then ensemble rainfall near mid far future will decrease due to climate change. So that is what is this percentage shows. and ensemble surface runoff for near mid and will decrease due to climate change. So this is a decrease, especially this river basin is concerned. So then combined impact of LULs and climate change suggests that a decreasing trend in near and mid scenarios for RCP4.5 with respect to 0.37 or 5.17 respectively. And then on the other hand, it is decreasing by 8.13 near and 4.66 in the some time slices it shows increasing, some time slices it is decreasing trend is shown. So the amount of stream flow is in monsoon season is predicted to decrease and become more severe in near future. The finding of this, so then summer rainfall, I mean during February to May, so that is recently in this region it is observed rainfall is increasing, and that impacts will be further carried over to the monsoon time also. So the finding of this study can give useful information for near, mid and far future ecosystem health and flood and risk assessment, and the water resource management and planning for long term should be so we can go for the various mitigation measures and adaptations as far as these details are concerned. So finally, to conclude this lecture, climate change is so not likely, but it is already happening. Impact most hydrological processes. Then impacts need to be assessed on a it's a country-wise we need to assess, then regional scale, and then if you want to see what is really happening. So if you say that for entire India this stage, but then we need to see what is happening in river basin scale. So that is what this case study shows. Smaller scales, GCM are the most credible tool, which how we can use the GCM data. That is what is shown here, and scale issues and uncertainties. So of course, the GCMs, what are the GCMs uncertainty, then the data uncertainty. There are so many uncertainties are there. So on a river basin scale, also these kinds of uncertainty studies we need to do, and results from the studies are useful in developing adaptive responses like long-term reservoir operation policies, modification, hydrological design, changes in cropping pattern, etc. And then we can also use similar studies in developing IDF relationship and the flow and duration curves accounting for climate change. So now when we discuss about the climate change, what are the major challenges with respect to hydrology? So the impacts, climate change impacts posed due to, so we can see so many impacts we can see with respect to the hydrology is concerned. So and then when it is not only climate, when the land use, land cover changes also takes place, the combined impact is very crucial as far as the river basin scale is concerned. So that we need to assess this kind of impact by considering all the uncertainties also, and then we have to go for further assessment and adaptation. So for sustainable development, conservation of water, minimizing wastage, in ensuring equitable distribution through integrated water resource management is essential. So that way, we need to put various goals for sustainable water resource management, like a comprehensive water database in public domain, then reliable assessment of impact of climate change. So that we are doing for as a project of Government of India, Ministry of Water Resource. So we are doing this for Tadri to Kanyakumari Western River Basin. So similarly, many other IITs and NITs are doing these kinds of studies for other river basins. Then promotion of citizen and state action for water conservation augmentation. So that way we need to look into the water resource management on an integrated way. Then focused attention for overexploited areas, especially groundwater in many areas are overexploited. So we need to go for groundwater recharge or what are the its impact studies also to be done. Then so of course, in a country like India, the irrigation efficiency is so low. We need to use how further increase the water use efficiency so that the water scarcity and all those issues can be sorted out. And then further promotion of basin level integrated water resource management is very essential as far as the hydrology is concerned. The river basin, especially river basin scale studies are concerned. So with this, I am concluding this lecture. So further, so I will be so happy to say answer to any of your queries. So especially the river basin scale, as I mentioned, is so important, these kinds of studies. So so I give back to the organizers for further proceedings as far as the question and answer session is concerned.
Thank you, sir, for the in-depth explanation. The field of hydrology is important now since it's dealing with one of the most vulnerable resource on earth, water. Thank you, sir. So participants can type your queries in the spreadsheets, which is already shared with you. Sir, we have already received some questions. So can we display it, sir?
Yes, please.
Okay, Shiba, you can start displaying.
Okay, the first question is in India, cities like Chennai, Shimla, etc. are going in the water crisis situation. Will the climate change increase the frequency of these events? So yes, as I mentioned, I can see that now this whatever the flooding or say whatever the assessment, you can see that in the AR5 and AR6, all the assessment shows that the hydrology will be very intensive. That means the precipitation is going to be high intensive in the coming years, and then more events, these kinds of events like the flooding, then droughts, and then also landslide. That kinds of events are going to happen, and so the of course, what as I mentioned, when rainfall happens, so mainly flooding takes place, high intense rainfall for short duration. That is the cause of flooding is concerned. But then the total rainfall will be increasing many areas. But whenever it is coming to afterwards, there will not be any rainfall for the next few months or like that. So that way, there is scarcity of water can also take place. So whenever heavy rainfall takes place, there is a possibility of high flooding, as you can observe in many parts of Himachal Pradesh, and then all parts of the country. So that is very much possible. So the frequency of these events are going to increase, as you can observe in this and all the studies in AR5 or AR6, and then further hydrological studies based upon that. So I hope I answered this question. Next question, please. Okay, the question is in India whether the water demand with and without climate change is the same. So actually, it is not same. Actually, you see, this is based upon some statistics based upon 2000, 2002 between 2010. But that changes. So here, as I mentioned, water availability. So for example, what was there in 2000 is if we are having 2000 meter cube per person per year, then by 2050, since our population is also increasing, that will be coming down drastically. So it will be becoming around 1000 meter cube per person per year. So that way, that changes, even though as you can see in that plot, it is small, but that plot is per person. That is, please remember, it is per person, whatever we put it. So, but that change itself, since already available, there is a water scarcity. Then, with respect to that, even climate change impacts also takes place. Then it is the effect will be very severe. So you can see that what is, though the precipitation going to increase, but whenever it happens in a very heavy way, it happens, then we cannot store the water in reservoirs. So that is what is happened in a state in Kerala 2018. You can see many of the dams which were they kept on storing the water, but when the heavy rain takes place, they have to release everything. So that also added the flooding problems. So that way, the problem is that whenever heavy rains takes place, it is for short duration. The number of events will be decreased, and events happens in a very severe way. So that way, the flooding will be the final outcome. So that way, as I mentioned, so here climate change impact is definitely there, but the per person, whenever you put it, that amount may be small, but that itself is too severe. Okay, I hope I answered that question. Next question, please. How is overexploitation of river basin impacting the groundwater table, river biodiversity, aquatic life, and overall hydrology of river beds? So here, how is overexploitation? Of course, as I mentioned, many of our river basins are overexploited. Say, for example, if you take Kaveri or Godavari or Krishna, all these river basins are overexploited. So that way, since we have got a number of dams and reservoirs, and then so that way, with respect to this climate change impacts are concerned, as I mentioned, what can happen is that so whenever we cannot store that much water, since the severe intense rainfall takes place for few events, and the total amount of rainfall may be higher, but whenever it takes place in say within few events, the storage possibilities, there is some limitation takes place, and that way this for the basins which are overexploited, there will be more severe impacts as far as the biodiversity, since the environmental flow will be decreasing, since as I mentioned, the climate change, that is whenever rains happens in few events and afterwards no rain, so that means the environmental flow will be affected. So that way, biodiversity, aquatic life, everything will be affected on a river basin scale. Okay, next question, please. So reservoir flow simulation, we can say here you see that reservoir flow simulation is concerned. We are having, so that depends upon the areas, like say we can have a number of models, like systematic, like based upon the like dynamic programming, linear programming, or the combination of all these kinds of models are possible. Reservoir flow simulation is concerned. Whatever, I hope this question is for the flow coming to the reservoirs. So here, that kind of simulations we can definitely do on river basin scale using the SWAT model itself. And then of course the VIC model, which I mentioned, it is a little bit more since it is grid based model. So but the SWAT model can give for whatever the inflows are coming to reservoirs. But reservoir now, the SWAT model is, and VIC models, we can also incorporate the reservoir aspects also, and then the models are modified in the recent times, and that we can put it for that kind of purposes. Next question, please. What are the methods that can be used for generating ensemble of climate projections, stream flows for different future scenarios? So here generating ensembles. So you see that we can say, as I mentioned, we need to first downscale the data, and then do a bias correction, and then based upon the particular GCMs. So that data, the different methods of, like you can give a the impact. I mean, with respect to grid wise, you can do a variety of methods are possible. So I think here we used with respect to the averaging of whatever is happening with respect to grid scale. That is what is done. So but we need to, so whatever the downscale data, so first we need to verify with respect to each GCM with respect to past data, and then if it is coming, the trend is getting better, then only we go for the ensembling with respect to say, as I mentioned, 5 GCMs which we have used for this river basin scale study. And out of that, for each basin, it is varying. So some basins it will be giving, some GCMs will be giving good results, and some other basins it will be different. So that we see, we observe that each GCM which we consider how is the performance, and then we go for the ensembling of with respect to that the best performing GCM. So for example, the details shown by shown in the paper earlier by which I have shown. So that is they are using around 16 GCM, and then another study is about 32 GCM. So a large number of to deal with the uncertainties related to the GCMs. Always better to use number of GCMs, and then identify which GCMs are giving better results, and then go for ensembling technique. So next question, please. Groundwater recharge was done in Maharashtra by the Satyameva Jayade water condas. Is that enough? So groundwater recharge. Of course, these are all small scale studies. We need to see large scale studies. Each river basin scale studies how much is the surface water, groundwater availability, and then whether we can increase the groundwater recharge through various schemes, like as I mentioned, watershed integrated water resource management, which is we are also talking about watershed management. Watershed management practices to be say become universal. So I mean, all areas we need to go for that, so that the good groundwater recharge can take place, and then many small studies are available with respect to the impacts of watershed scale intervention as far as groundwater recharge is concerned. Next question, please. Are there any uncertainties involved with these simulation models? If yes, then what are the major factors? Of course, as I mentioned, uncertainties, there are so many uncertainties are there with respect to the GCM uncertainty one, that is a climatic data is concerned, then the data uncertainty, whatever data we are using, and then of course model uncertainty is also there. So for example, if we are using So SWAT model where we use number of assumptions, and it is semi-distributed model, or if we are using VIC model or MITC model. Each model has its own assumptions, and that model uncertainty is also very important. So these uncertainties, it is always better to, so anyway, if you are doing comprehensive studies, it is better to study the model uncertainties also. So that way, whatever the SWAT model gives or VIC model gives, there can be some differences. So that kind of uncertainties also, it is always better to take into account while considering these kinds of river basin scale studies are concerned. Yes, next question, please. For SWAT, what will be the right choice of calibration and validation time period for a precipitation particular time scale? So here, as I mentioned, say if you are having a large data set, I mean reliable data set, so then say generally minimum we prescribe at least minimum 6 years calibration minimum. So if you can go for 10 years, that will be generally good enough. So 6 years, even 6 to 10 years will be good enough for calibration. And then so especially we are doing daily scale we are using, and then we can validate for another 6 to 10 years. So that is the general trend is there, but the minimum 5 to 6 years is required. So that is the minimum requirement, and better is going up to at least 10 years. So since we are using this model for further up to 2100, so that is why I'm saying at least minimum 10 years or 6 to 10 years data for calibration and validation. Further, I mean 10 years for calibration and 10 years for validation. That is the best choice. And but if you are having better data, then that will model confidence will be increasing, so that we can use for further maybe 10 to 15 years also if it is available. But average say 5 to 10 years data is required for calibration and validation. Next question, please. Of course, the last question part is that, of course, the river basin is also important. If it's small river basin, then the data requirement will be the calibration validation with the data, the years can be reduced. But for larger river basin, it is better to go for a longer span. And next question is how can we study SWAT on river interlinking projects? So river interlinking projects are concerned, of course, what we do. So as you can see that our plan is to transfer river, the water from one basin to another basin. So for that, we need to assess each river basin separately, and then whatever how much water is water surplus is available or not, and then based upon that only we can decide. So that is a major issue. So we need to study each river basin, is historical past data, using past data, and then projected data up to 2100, and then only we can take these kinds of studies. So each river basin scale studies is very essential for river interlinking projects, so that SWAT model we can utilize, or other kinds of models also we can use for this kind of study. So first we do past the historical data, using historical data, and then the projected data can be used, and so that whether it is consistent trend is there, or whether after a few decades whether it is going to drastically reduce, then the river interlinking may fail. So that is the issue. So we need to see with respect to the past historical and the future projected, and then for each river basin whatever to be interlinked we have to study, and then we can see that whether surplus water is available or deficit, how it is, and then we can do that. Will be the best way to do this. Next question, please. Any other question, please? Yeah. So how we can check the our results of rainfall trend analysis, whether it is wrong or right? So what we do, so the best way is that so the climate change is concerned, generally we put a time span of 30 years. So what we do, say for example, whatever in our analysis, say for example 1980 to 2010 data, whatever the rainfall data what we obtained from IMD, so that data we are used for the checking whether it is getting good trend or not. So that is, as I mentioned, each GCM data we can get from when all the simulation start 1980s or 90s onwards up to 2100 data we can get it. So what we do generally, the climate change studies are concerned, generally we use for 30 years span. So for that 30 years span, so we can take 80 to 2010 or 90 to 2020 or whatever with respect to your data, and then we check the let's say India is concerned, IMD data will be using that data, and then what is the GCM data is getting, and then we will be using whether further bias correction is needed. So if the bias is there, then we will be doing like the particular method we will be using for bias correction, and then we will be, if we are getting good correlation, then that data can be used. So generally, rainfall trend analysis we have to do a 30 years time period, and if it is getting good trends, then that data we presume that yes, whatever the data getting is good, and then that GCM data we can use for further projections and further studies. Next question.
So we don't have more questions, and
Okay, fine.
okay, sir. So we can wind up this section. Thank you, sir. Thank you all. Tomorrow we have a talk by Professor Basudev Biswal on climate origin of hydrological responses. Thank you, and see you all on tomorrow's section.
Okay, thank you very much.
Thank you, sir.